Hello, welcome to this lesson on our study of fluid dynamics. Okay, so in this lesson, I will take you through what we call the Reynolds transfer theorem (RTT), and also continue to the conservation of mass in the Reynolds transport theorem. Okay, so if I have a system, okay, it talks about a system and how fluids flow through a system. Okay, so in here, let's say that this thing that I have here, this box here, is my system. Okay, let's say it's my system. Then whatever that is inside here, or the inside of the system here, is what we call the control volume. Okay, so you should know these stuffs: control volume. Okay, and on the boundary here is what we call the control surface. Okay, so control surface. Okay, now knowing these, the certain terms I want you to know. Okay, in Reynolds transfer theory, we actually deal with the extensive property of a system. Actually, basically the idea is we are trying to find the quantity of the system, or the quantity of the material or the fluid that is flowing through. Okay, basically that is how we are. So the formula for the extensive property is this one here, that B is equal to, let me use the green one here, B is equal to MB, where B is per unit something, okay, per mass. It's a specific quantity, so you can make B the subject. Small b is equal to capital B over mass. Okay, so for every extensive property, something like let's say velocity or anything like that, okay, the velocity is equal to MB, and then the M will be something. M is mass, and B, we can make B the subject from that equation. Okay, and now we have this equation here that I've circled with the real red pen. Okay, so this one that says KO is equal to UA. Here KO is known as volume flow rate. Okay, volume flow rate. You can keep this, or discharge. Okay, is the same as volume flow rate. Okay, but most books prefer the discharge. And so now if I have a system like what we've talked about here, with this box having the control volume, control surface, then the change in the the change in the extensive property per change in time. Okay, I'm talking about the equation down here. Okay, is giving us d dt of the integral b small b times rho, and rho here is the density of the material. Okay, I was supposed to go through the proof to you, or to help or aid you in learning this, but then the proof is very long, so we'll take our time and one day go through it together. Okay, so this is the b here is from this b. Okay, and then we have the rho, which is the density of the material or the fluid we are studying, and u is the velocity of the fluid, and dA is a small change in area. All these stuffs, the first part is from the control volume part, I mean the inside of the system. Okay, then plus summation of b small b, we know it, rho we know it, u we know it, and area. Okay, here we are using this sum, not integral, because you considered the surface here to be smooth, and it's very uniform, and yeah, like that, or can be steady as well. Okay, we're considering a steady something. Okay, now the summation part is also from the control surface, meaning we are summing the quantity of the fluid, this small b, at the surface of it and at the surface of entering and exiting. Okay, and then we'll multiply it to the velocity of the entrance and exiting, and area of the entrance and exiting. Okay, now I've written something here. I want you to pay attention to this part. It's very important. I've circled some minus here, and some plus here. So with the entering, okay, any fluid that is entering the system, we give every property of that fluid a negative sign, or everything after summing everything, we give B to be negative for entering. Okay, that is entering and exiting. Okay, so if this is a system, that is it for exiting, we have plus B for exiting. Okay, so it means that you go to the control volume or the control surface areas, then you know where fluid is entering, you assign negative sign to whatever calculation after you are done, and where fluid is coming out, you add positive to it. So knowing this formula, let's keep it in mind. Okay, let's keep this formula in mind. Actually, you might not be needing the whole of this formula, yeah, but it's nice if you know how we get our mass equation. Okay, so continue. Now you have conservation of mass. So from this equation that we have here, this looks very nice. Okay, it looks very nice. Now if I want to write my B, we are saying that B is equal to what? Mass, okay, times B, MB, then over delta T should be equal to D dt, integral of the control volume, then B rho U dA, plus summation at the control surface B rho UA. And we are saying that the discharge here is equal to U times A. Okay, so you can actually write this charge here if you want, but let's keep it this way. Okay, now if you consider this clearly, if you consider this very thing clearly, and you are saying that, say, B is constant. Okay, if B is constant, then it means that this delta MB here, since B is constant, we can factor B out and we get something like B. Okay, we get something like B delta mass. Okay, since B is constant, you can take it out from the delta sign, then delta T is equal to B is a constant, so I can take it from the integral and then the differential equation or signs. Okay, plus here too B is constant, so I can do this rho A. Okay, now having these, okay, let me try to divide through the whole of this equation by B. If I do so, here will be divided by B and this will take this out. Okay, I hope you get it. The whole of this will be divided by B and this will take this out. This will be divided by B and this will take this out. Now what are we having here? We have only delta M. Okay, delta M delta T is equal to d dt integral rho U dA plus summation rho U A. This is happening at the control volume, this is happening at the control surface. So now, since we have only D of mass d something, this is the equation for the conservation of mass in the Reynolds transport theorem. Okay, so this is very simple. We're going to take examples and solve them. Kindly pay attention to what we'll be saying, because some of the examples are very simple if you know your flow phenomenon very well. Okay, so in our first discussion, you said something about steady flow, uniform flow. You're supposed to also know them as well before you can relate to this. Okay, so let's move ahead and solve two examples and we'll be done for this lesson. Okay, so we have, suppose water flows in a tank as indicated in the diagram below from point 1 to point 2. Okay, so it flows, as in it starts entering this tank from point 1, so we have negative in the intrinsic, and exit the tank at point 2, so we have positive. So you should always keep these in mind. It's entering and it's entering at point 1, and this is also, exiting at what, point 2. Okay, so if the diameter of the entrance is 10 centimeters. Okay, so let's say at the entrance we call it D1 is what, 10 centimeters with a flow rate of 10 centimeters per second. When we have length per second or length per time, it means we have what, velocity. So u1 at the entrance, so we are calling it u1 is equal to 10 centimeters per second. Okay, the diameter at the exit is 15 centimeters, so d2 is equal to 15 centimeters. Find the fluid velocity at the exit, so we are supposed to find u2 given that the flow is steady and the mass of the water does not change. The mass of the water does not change. Now, this is what you are supposed to know. Since we are being given diameters, okay, it means that we are assuming that the entrance and the exit are both of circular in nature. Okay, so the area at which the fluid is entering is circular in nature, and the area at which the fluid is exiting is also circular in nature. Okay, so let's go ahead and try to solve this. So from this previous one, we said that mass is constant in the question. Okay, the mass of the water does not change. It means mass is conserved. When we say something is constant, it means mass is the thing is conserved. So you're going to use this formula, okay, to solve our question. So quickly, let's write the formula down. We have delta m delta t is the same as dm dt. Okay, then d dt integral control volume rho u dA plus summation control surface rho u a, and these are what we have for the conservation of mass. Okay, now we are saying that the flow is what, steady. Okay, given that the flow is steady. Okay, so here the flow is steady. Now with a steady flow, it says that the fluid property, something like density and the rest, does not change with time. Okay, so whatever fluid property that we have, meaning if it is extensive property, the change of the extensive property with respect to time is zero because it hasn't changed with respect to time. So if I differentiate it with respect to time, it becomes zero. In other words, it's like the extensive property in steady state or steady flow is always constant. Okay, so it doesn't change. This means that delta m delta t is zero because mass is an extensive property. Okay, and also ddt, if you remember, ddt of the whole of this, because this, there is a differential sign here. Okay, we are differentiating the whole of this with respect to time, and we are seeing that it is equal to zero as well. So we have 0 equals summation control surface rho ua, meaning whatever that is happening at the surfaces. Okay, so in the first place, what you do is, you know that d1 is equal to 10 centimeters. Okay, given the question, u1 is also given as 10 centimeters per second. Okay, and d2 is given as what? D2 is given as 15 centimeters. Okay, 15 centimeters. But I don't know u2. This is what you want to find, u2. Okay, so let's go ahead and write a very simple equation for it. Okay, so for the first surface, for the entrance surface, okay, what will happen? For the entrance surface, summation of control surface rho u a will be equal to, now we are calling the entrance things to be rho 1 u1 and a1. We have rho 1 u1 a1. Okay, and this is negative. We are saying entering is negative, so we have this. a1 for the, so let's say point 1 at point 1, let's call it that way, or we can actually say this. Let me use a white pen for it. So point 1 here. Now at point 2, summation control surface rho u a, okay, will be equal to rho 2 u2 a2, and this is equal to rho 2 u2 a2 as well, because it's positive. Okay, so you can put a plus there if you want. Sorry, this is at point 2. Now we have u1 in the question, but what we want to find is u2, and we don't know a1 a2, we don't know rho 1 rho 2. But I said that in a steady flow, the extensive properties are they are constant, they don't change. So it means that rho 1 will be the same as rho 2. Okay, so we keep this, and we can call them, let's say we're calling the whole of this rho, we are calling all of them rho. Okay, now we are saying that the area at which the water enters or exits, they are all both circular in nature. Okay, so what is the area of a circle? The area of a circle is given as pi r squared. Okay, now we're not given r, so we're supposed to find our answer in terms of diameter. Okay, but diameter is equal to 2r, or you can say that r is the same as diameter over 2. Okay, let me put it that way. R is equal to d over 2. So if I substitute everything here, I'll get pi d over 2, which is the r squared, and this is pi over 4 d squared. Okay, so we keep this. It means that my area 1 is equal to pi over 4 and diameter 1. So we go to d1. D1 is what? This, which is 10 centimeters. But centi, we don't want to work in centimeters. We have to change the centimeters to meters. But centi means 10 to the negative 2. Sorry, yes, 10 to the negative 2. So it's like 10 times 10 to the negative 2 squared. Okay, like that. And this will give me pi over 4 times, then you take your calculator, you can punch it on your calculator. I'm doing mine on my calculator, so I have 10 times 10 to the negative 2, then I square it. Okay, so this will give me 1 over 100, and the same as pi over 400. Okay, then meter squared, that is the area 1. So I'll go to my area 2. Okay, let's go to A2. Okay, so now with the second area A2 is also equal to pi d2. Okay, so d2 over, or let me write it this way, pi over 4, now d2 squared. Okay, this means that we have pi over 4, d2 was given as 15 centimeters, which is 10 to the negative 2 meters. 15 times 10 to the negative 2 meters, so squared, and this will give me let's point 15 times 10 to the negative 2 all squared. Okay, 15 times 10 to the negative 2 squared, and I have here 9, so this will be pi over 4 times 9 over 400. Okay, meter square. So I just have to, is it 400? Oh, okay, all right. So I have something like, if I multiply them, I'll get A2 is that. So I have pi 9 pi over 4 for 16,600 meters squared. Okay, to be my A2. So I have A1, I have A2. Now let's go ahead and find, U1. Okay, so let's see. So what this whole thing means is that from what we wrote here, okay, from what we wrote here, that the summation of all the extensive properties on the surface, control surface, should be equal to 0. It means that all the extensive properties or all the summations I've done on the entry P1 plus P2 should be equal to 0. Okay, so we go and say that the summation of the P1 was negative rho 1 mu1 U1 A1 plus rho 2 U2 A2 should be equal to 0. This is what it means. Okay, and now with this we said that rho 1 is equal to rho 2 and is equal to rho, so I can put it here and get something like rho U1, because rho 1 and rho 2, they are the same, they are also called rho, plus there's a minus sign already here, rho U2 A2 equals 0. Now if I divide through by rho, I will get something like negative rho U1 A1 plus U2 A2 equals 0. And now with this, I know my U1, I know my A1, I know my U2. Sorry, I know my A2, but I don't know U2. So we are finding U2 rather. So this becomes a simple linear equation for us to solve. Okay, this is very simple. So with the help of linear equation, let's try to make U the subject, U2 the subject. Okay, I can send U1 to the other side of the equation. I'll get U2 A2 is equal to U1 A1, since they are both negative. Okay, so I have my U2 being equal to U1 A1 over A2. So simply my U1 was given as 10 centimeters per second, and this is the same as 10. You said centi is 10 to the negative 2 meters per second. So it's very simple. You don't need to do any calculation. Know that centi is that, and that is all. So it means that my U2 here will be equal to U1 is 10 times 10 to the negative 2, then times A1. Then we are saying A1 is what? This is A1, okay. Pi over 400 meter per second. Sorry, meter squared. So pi over 400 meters squared. I don't have to bring the meters yet. And my A2 is also given as what? A2 is down here. 9 pi over 16. Okay, so 9 pi over 16. So I have 9 pi over 16. Sorry, 1600 rather. And so this here, it becomes very simple for us to solve. You can point the whole of this on a calculator if you want, but let's leave our answers in pi and see. So I have U2 being equal to 10 times 10 to the negative 2 times pi over 400 times 9. Sorry, this changes to be 1600 over 9 pi. And so pi can take pi out. I have 400 going to here 1. 4 for 16. So I have times 4. I have this. Okay. And now I'll get something like U2 is equal to. Now I have 10 times 10 to the negative 2. 10 times 10 and it's 0.1. But let's confirm that from a calculator. Okay, so 0.1 times 4. So I have 0.1 times 4 over 9. This will give me what? Times 4, and that is 0.4 over 9. okay, which is equal to 0.0444. So let me say 0.04 meters per second. Okay, so this is very simple. This is how you find your U2. Now let's go ahead and solve an additional question and we'll be done for this lesson. So given that water flows through the tank above and the flow rate at point 3 is recorded as Q equals 0.01 meter cube per second. So we'll find the velocity at point 2. So at this point, okay, given that the mass of the water is conserved and the flow occurs under steady condition. Sorry, the steady here is supposed to be STEADY. Okay, I'm sorry, I made a mistake there. Okay, so here, very quickly, the same thing applies to the sense is steady. We are going to conclude that first, the t or the integral of rho. We are using mass conservation. Let me explain this before I continue. Now we are using mass conservation because they said that mass of the water is what? Conserved. So since the mass is conserved, you have to use an equation that we know in conservation of mass. Okay, so with that said, let's go ahead, and we are saying that since it's steady, anything differentiated with respect to time is equal to 0. Delta m delta t is also equal to 0, and here what we'll be left with is 0 is equal to, we are putting every equation, 0 plus summation control surface rho mu, or u is u rather, is no mu, ua. Okay, now at point 1, so at point 1 we have the summation as point 1 to be rho 1 u1 a1. Okay, and let's go ahead and see something. Point 1 we are entering, okay, at this point is entering, we're entering the system, so it means we have a negative attached to it. At point 2 we have, okay, point 2 is just going outside, it's exiting, so we have u2 u2 a2. Okay, at point 3 we have negative u3 u3 a3. Now let's go ahead and see point 3 is entering. That is why I just did it like that. Okay, so that is it. Now you say that given that water flows through the tank above and the flow rate at point 3, okay, so at this point flow rate Q is equal to 0.01 meter cube per second. Okay, and flow rate is given as what? Okay, I want to establish something here. Flow rate Q is equal to UA. So at point 3 Q is equal to what? U1 A, sorry, U3 A3. Okay, that is at point 3. So it means that this U3 A3 has been already given. Okay, so Q at A3, Q at that was given as 0.01 meter cube per second. So we are done with this side. Okay, now what we want is U2. Okay, so you're supposed to find A2, A1, U1. Since it is steady, our density is also constant. Okay, so let's write that rho1 equals rho2 equals rho3, and we are naming it rho. Okay, so we are supposed to find u1, a1 and a2 just like that. Okay, so let's go ahead and see. But in the question we're being given u1 is what? 3 meters per second. Okay, u1 is 3 meters per second, so you can write it there. u1 is 3 meters per second. Now a1 will be equal to, from our derivation we did, pi over 4 d1 squared, and this is equal to pi over 4 d1. Was it given? So we go to the question and see d1 is also given 5 meters per second, sorry, 5 centimeters squared. And so 5 centi is 10 to the negative 2, okay, squared. And this will give us, now we take our calculator and point 5 times 10 to the negative 2, then we square it, okay, and get something like 1 over 400. Okay, so we have pi over 4 times 1 over 400, and this will give me pi over 1600, okay, meter squared. We said we also need what? Sorry, we also need 8. U2 is what we want, so we also need A2 as well, okay. So A2 is also equal to pi over 4 d2 squared, okay, and A2 will be pi over 4 d2 is what it was given, okay. D2 is this 7 centimeters squared, and this will give us 7 times 10 to the negative 2 all squared, and this is equal to, so I have 7 times 10 to the negative 2 squared, and I'm getting 49 over 10,000. Okay, so let me write it here. Pi over 4 times 49 over 10,000. Okay, and this will give me 49 pi over 10,000. Sorry, 40,000 rather, because you are multiplying by 4 down there, meter squared. Okay, so all that we need, we are done. Now let's go ahead and check the equation we write. This is what we, at point 1, the summation at the boundary was this, so we add this is minus, and we add point 2, which is plus, we add at point 3, which is also minus, and we are saying that it should be equal to this 0. Okay, so let's see, minus real 1, okay, let me see, real 1, then u1 a1 plus real 2 u2 a2 plus or minus, let me see, minus real 3 u3 a3 should be equal to 0. We are seeing that u3 a3 was given as q3, so we don't have any problem, and real 1 equals real 2 equals real 3, and is equal to real. Okay, so you have real u1 minus of that a1 plus real u2, they are the same, so we are just writing this real q3. Okay, this is equal to 0, so this take that. Okay, we just divide through by real, and that is it. So we have u2 here, a2, I'm sending everything to the other side of the equation, and I have q3 plus u1 a1, okay, then u2 will be equal to q3 plus u1 a1 all over a2. Okay, now I just go ahead and substitute in my values, okay, just like that. So let's calm down here some more. So we have this u2, let me change the color for you. u2 will be equal to q3, so you go to q3, I'm saying that q3 is equal to the u3 a3, and that is 0.01 meter cube per second. Okay, it was given in the question here. Okay, alright, so that is it. Let me circle it for you. It was given that the flow rate at 0.3, that means q3 is that. Okay, so 0.01 meter cube per second. Okay, so 0.01, then plus u1 is what? u1 is given as 3 meter per second. Okay, so 3 times, then we have this thing a, let me see, a1 to be pi over 1600. Okay, so I have pi over 1600 all over, I go to my a2, which is 49 pi over 40,000. Okay, so 49 pi over 40,000, like that. So whatever answer that we get here will be our final answer. Okay, so let's see, let me write the answer here. So u2 will be equal to, then you take your calculator. This is very tedious work, so I don't want to go through it. 3 times, you have 0.01 plus 3 times the fraction pi, I'm just substituting them, over 1600 over 49 pi over 40,000. Okay, and this is giving us 4.129 meter per second. This is my solution. Okay, very easy, very simple like that. So whenever the question is being given, all that you have to do is check, write your formula down. You know that the formula is always given as this. The formula is always given as this. Okay, where is it? I want you to write the formula first. The formula is always given as this. Okay, so after writing the formula, this one, okay, this one. Now after writing the formula, what you do is you simply just search for which part will be 0, which part will maintain. So you see, the questions that we were solving, almost all the time this part and this part were 0. Okay, they were zeros, but it can be that they may not be 0. Okay, so just check the type of flow you are dealing with. Is it compressible? Is it steady? Is it what? Okay, like that. So that is the solution to these questions. Thank you, and don't forget to subscribe to my channel if you have not subscribed. Thank you once again.